It's my privilege today to introduce Peter Balsam. Peter received his bachelor's degree at Stony Brook and his PhD from the University of North Carolina at Greensboro, both of which gave him a strong dose in the operative tradition. He moved on to Columbia University, where he has stayed ever since, and is now the Samuel R. Milbank Professor of Psychology there. He has a long history of funding with NSF and NIH. He has served as the chair of his department and is currently the director of the Neuroscience and Behavior Program, and he also chairs Columbia's IAPA. Additionally, Peter has served as the president of the Eastern Psychological Association, and he's a fellow of just a gaggle of different associations. He has served on a number of NIH review panels and for a number of years chaired the BRLE study section. Peter's research was initially hardcore operant, focusing on traditional issues such as reinforcement, auto-shaping, and negative auto-maintenance. But refusing to be captive to any one paradigm, he soon discovered that at least some questions might better be answered in a Pavlovian preparation. His greatest contributions over the years have been concerned with the development of acquired responding, how animals time stimuli and time intervals between stimuli, and now he has turned to studying the neurophysiological basis of time and behavior. A common denominator across all of the work is that behavior does not happen in a background. He's consistently been concerned with the role of the experimental context. But the real consistent feature of Peter's work over the many years that he's been in the laboratory has been the extraordinarily high quality of his many contributions. Today, Peter has agreed to provide us with a tutorial titled Time, Uncertainty, and Anticipation, foreshadowing what's going to happen, time, 50 minutes. I'm uncertain what he's going to talk about, but we all await with much anticipation. Peter?
Thank you, Ralph. So I'll start by talking about time. I am also uncertain about what I'll say, and we'll get to anticipation. So, all right, first I want to thank a number of people. A lot of people contributed to the ideas and to the data that I'm going to show you today. And it's really been something that I've been interested in over a very long time, and I keep trying to move away from some of these questions and then always come back to them, because I think there's something very fundamental about the way that time organizes behavior. So behavior is organized on a number of different scales. So there's circadian timing, which is on the order of days, 24-hour periods. And there's actually a fair amount that's known about how that works, both at a functional level and at a biological level. Then there's interval timing, which is in the range of seconds to hours. And I've lumped that all together, though I'm not really convinced that's a single mechanism. And then there's rapid motor timing on the order of milliseconds. And so there are at least these three distinct kinds of timing mechanisms, and probably more. And what we're going to focus on today is interval timing. And interval timing is everywhere. It's ubiquitous. In foraging decisions or decision making, it requires estimations of how much time is passing. In order to make a good decision, you not only have to know what to do and when to do it, what to do and where to do it, but you also have to know when to do it. Anytime you anticipate something, it implies that you have an understanding of when something is going to happen. You have a memory of how long it's taken in the past. And even simple associative learning, when you just have a conditioned stimulus paired with an unconditioned stimulus, seems to involve the learning of temporal information. And what I want to throw out, I guess, for discussion today is sort of a radical view, which is that associative learning is learning time. So, to begin, let's start with the traditional view. And like a good introductory psychology textbook, we start with Aristotle, who actually, even though the intro psychology books tell us that Aristotle was talking about formation of associations, he was actually talking about what makes for good reminder cues. In his essay on memory and reminiscence, he said that things that in the past had appeared contiguously, either temporally contiguous, close together in time, or close together in space, one thing would be a good reminder cue for the other, or two things that were similar, one would remind you of the other, or things which even contrasted with each other could be good reminders. And about 2,000 years later, the British empiricists were trying to make the case that all knowledge comes from experience, and they needed some mechanism, some machinery that would allow that to happen. And so they posited that sensations got glued together through associative processes, and the sensations got put together to create ideas, and ideas could get put together to create more complex kinds of thoughts. And they borrowed the idea from Aristotle that there were primary laws of association: contiguity, similarity, and contrast. And then what they added into that, particularly Thomas Brown, were the secondary laws of association, which were frequency. The more frequently two things appeared together, the better connected they would be. Duration of exposure, and what he meant by that was that the more they overlap with each other, the more they're presented at the same simultaneously, the better one would remind you of another. Liveliness, which we would probably call salience, was another one. So when things were salient, they would get connected. And recency. So things that you've seen go together recently in the past were better connected than things you might have seen a long time ago. And Thomas Brown had a very good friend, right? And psychologists began to claim that the foundation of knowledge and learning was the formation of associations. And whether it was Ebbinghaus or Pavlov or Guthrie, Tolman, Hull, other people, your favorite associationists, they differed about what had to be contiguous with each other in order for associations to form. So some of them claimed it was contiguity of two stimuli, or contiguity of a stimulus and a response, like Guthrie, or response-outcome associations is a kind of a more modern view of it. And they also differed on what was actually learned. So what was learned were associations between stimuli, or stimuli and responses, or responses and outcomes. But what they all agreed on was that contiguity is what underlied the learning, that these things had to be contiguous for these connections to get cemented. All right, so then in the 20th century, we went ahead and we started to experimentally analyze the formation of associations. And so why do we believe that contiguity is important? So the kind of experiment was the type that Pavlov did, where a conditioned stimulus was paired, say a tone, was paired with an unconditioned stimulus, food. The food elicited salivation, and after a number of those pairings, the tone came to elicit the conditioned response. And there are a lot of different preparations people have used in order to study the formation of associations. And here's one that was pretty popular for a while, which is known as auto-shaping. And in auto-shaping, which we'll see in a minute, I hope, in auto-shaping, the conditioned stimulus is the illumination of a little light, and the subject is a hungry pigeon. And the pigeon has learned that food is presented in this food hopper down here. And as the experiment progresses, the little light comes on, and a few seconds later, it's followed by food, and the bird eats. And after a number of those pairings, the bird will, when the light comes on, I'll skip ahead a little here. When the light will come on, the bird will eventually peck. And what we've taken as our evidence of learning is when the little light comes on, the bird will go over and peck at it, kind of like it's food. And so what we can do is we can look at how many pairings it takes of that key light with the grain before the emergence of this anticipatory response. And so if we were an inch there, the bird's pecking at it. This is a very reliable thing. And so what we can do if we're interested in studying contiguity, we can vary the contiguity, say, between conditioned stimulus and the unconditioned stimulus in some way, and just see how long it takes for the bird to appreciate that the light is a good predictor of food. So in the two kind of standard procedures in Pavlovian conditioning that people use to study the effects of temporal variables or delay conditioning, where a conditioned stimulus comes on, stays on until an unconditioned stimulus is presented. So that would be the key light comes on, it stays on until food's presented. And the way we can vary contiguity is we could just have this key light turn on earlier and earlier. That would be one way of varying the contiguity of the onset with the food. Or another way we could do it is we could take the cue and keep the cue duration the same and just slide it back in time so that there's a gap from the offset of the cue until the food is presented. And that's called trace conditioning. And when people have done those experiments, and there have been hundreds, if not thousands of these experiments, the result is pretty consistent. So here's an example of delay conditioning. These were auto-shaping experiments in which the key light was either 4 seconds or 8 seconds or all the way up to 32 seconds. And it was followed by food. And this is the median number of trials it took the birds before they treated the key light as a good signal for food and went over and pecked at it reliably. So when it was 4 seconds long, it took about 20 trials before the bird pecked at it. And when it was 16, maybe 70 trials, and about 150 trials when it was 32 seconds long. So it took longer for the bird to start to respond. In trace conditioning, there's a similar, I went too far, okay? In trace conditioning, we have a similar result. So this is an example of a conditioning study. It was done with rats, similar to the one with pigeons, where in this case a tone came on for 6 seconds, and then the tone went off, and 6 seconds later it was followed by food. That was one condition. And what we measure in this case is the rat going over and sticking its head where the food's going to appear. So in anticipation of the food, it puts its head into the food hopper, and we get a lot of anticipatory responding with this 6-second gap. But if we turn the tone on for 6 seconds and then wait 18 seconds before presenting the food, we get a lot less responding to the food hopper. And so the usual way we look at this is that we say that there's weaker learning when the gap is long compared to when the gap is short. Contiguity affects the learning. Right? So today, though, I'm actually going to challenge that, because animals learn over delays, and sometimes they learn over very long delays. And so first, here's the truth about trace conditioning. So, as I said before, when there's a short 6-second gap, they respond a lot to the tone, but when there's an 18-second gap, they respond a lot less. But if you actually look at what they do during the gap, what you see is that they've learned those intervals perfectly well. They know exactly when the food is coming. It's true that during the tone, they respond less when there's an 18-second gap than when there's only the 6-second gap. But if you look at what they do when the tone goes off, they respond even more after the tone is off in both cases. And so it's true their level of arousal or their level of excitation about the cue might be higher for the shorter delay to reward, but they know when the food's coming. They've learned it perfectly well. So I wouldn't want to take this as evidence that contiguity actually changed the learning. I think they learn well in both cases. And it gets worse. All right, so there are lots of examples, and many of you in the room will be familiar with them, in which animals learn very long delays to reinforcement. So here's just one example taken from a study by Pizzo and Crystal, in which a cue came on, and then 3.5 hours later for a bar press, the animal earned a meal. And what does the animal do? The animal learns that a 3.5-hour delay just perfectly fine and responds more and more as the time, toward the expected time of reinforcement. And there are lots of examples of animals learning things in hours range. But it gets even worse. All right? So not only do they learn these long intervals, but what they do to cues that signal the long intervals can change based on the interval. So here's a study that was done by Peter Kaplan a long time ago. And in this particular experiment, what he did was he varied the location of the key light with respect to the food in one of these kind of auto-shaping experiments. So in one case it was very close to the food, and then he put in a bigger gap, slid the cue back, he slid it back even farther. And so he varied the position of the cue in the time in the cycle between food presentations. And what he found was when it was close, the bird would in fact go and approach the key light and peck at it. And when it was back further, it might approach it. But what it did when the key light was all the way back in the middle and even further back is it would look at the key light and it would turn around and run to the other side of the box. So it wasn't a failure of learning. If we had only measured pecking at the key light, we'd say that the animal didn't learn about the cues when they were further back in that cycle. But in fact, what the animal was doing was it has a tendency to withdraw. So here's just as a function of the proximity to food where the signal was, whether or not the animal approaches it or withdraws from it. So the actual response changes. Well, it's even worse than that, actually. Bill Timberlake has been providing lots of evidence that as proximity to food changes, search modes change. So initially, let's say there's a cue that's pretty remote from the food, the animal will engage in search behaviors, general search behaviors like walking around. When it gets a little bit, if there's a cue that signals you're a little more proximal to food, it'll engage in focal search, like getting very close, maybe looking in the feeder, and then handling and consumatory responses when it's in proximity. But you almost didn't have to do the experiment to know that contiguity really wasn't affecting the learning, but it was changing how that learning was expressed. So imagine, I'll just do a thought experiment, right? So imagine that half a second before I do it, before I throw a baseball in your face, I tell you. So what do? You blink. But imagine I tell you 2 seconds before that I'm about to throw a baseball in your face, you duck. And imagine 5 seconds before, well, I'll make it a little longer. Imagine 30 seconds before I throw a baseball in your face, I give you a signal, I'm going to throw a baseball in your face. You hit me, right? Or you do something else. And the difference between those conditions is not a difference in the strength of the learning. It's really in how that learning is expressed in different response forms. All right, so what I want to turn to now is really to document that time is learned in Pavlovian conditioning. So what we've seen so far is that when delays along the low level of excitatory responding is not a failure of learning, it's an adaptive expression of learning about times. And sometimes the form of the response may even change with the delay. So how general is learning about time in these kind of procedures? And when is it learned? Is it something, Pavlov thought it was not something that was learned immediately, but he thought it was something that was only learned very gradually. But I think we'll see in a few minutes that's not the case. All right, so how do we study timing? One procedure that's been very useful to us for studying timing is something called a peak procedure, which has two kinds of trials. One kind of trial, a cue comes on, these are fixed interval trials, and when the cue comes off, a reinforcer is presented. We can either require the animal to make a response, or if it's a Pavlovian procedure, we can just pair the cue with the reinforcer. And what happens typically is the kind of performance that I showed you before from the piezo and crystal, which is that the animal responds more and more toward the end of the cue. But we don't know if the animal actually knows the time. Maybe it just responds more and more until it gets food. The way we know that it actually has learned the time is we throw in these other kind of trials where the cue comes on and it stays on for a very long time, but it's not reinforced. And what happens then is the response rate goes up to about the expected time of reinforcement, and then the likelihood of responding decreases past that point. And so if we average over trials, what we see is that there's an increase in response rate up to the expected time of reward and then a decrease. And that way we know the animal is actually timing here. So here, for those of you who don't do this, here's our star mouse. And the star mouse now is having a fixed interval trial. The bar just came out over here, and that signals the beginning of the trial. This mouse is on a 30-second FI. And while you think the mouse isn't paying attention, you'll see in a minute, but it is. So it comes back down, makes a few presses, and works away. Food is delivered, and it goes and it eats. Okay? So now, here's what happens on the peak trial. And you'll see why this is our star here. So this time the mouse has eaten the wood chips. The bark just came out. That signals the beginning of the interval. And now the bar is going to stay out. There's going to be no reward delivered. So what we're interested in is when does it begin pressing at the bar, and when does it, and then when does it stop pressing at the bar? And if you weren't convinced that the animals actually time before seeing this, at the target time, the mouse actually goes and looks for the food that wasn't presented. It's really a remarkable and very reliable behavioral assay for what's controlling the animal's behavior. This is interesting. If you could see my screen, what you would see is peak curves. Let me just do it anyway. There you go. Okay, what you would see is peak curves, which are the rate of responding during trials for cues of different duration, were reinforced at different durations. And there are humans over here, and there are pigeons over here, and there are mice over here. And what you can see is that the peaks are at different times. And the peaks are about the reinforced times in the different experiments. And one of the properties of this kind of interval timing is that the standard deviation increases proportionally with the mean. And so when they're rescaled, all the different times superpose on each other. That's known as a scalar property. And it's a characteristic of this kind of timing. So this tremendous species generality in terms of the underlying timing mechanism that's involved here at a functional level. Oh, there it is. Right. Okay. Well, yeah, here's here's eye blink conditioning in rabbits. And here, cue comes on, 125 milliseconds later, there's a shock around the eye, and in anticipation of that shock, the rabbit blinks. When it's 250 milliseconds, here's the peak magnitude of response. When it's 500 milliseconds, and when it's 1 second, it's out here. So eye blink conditioning is timed. Here's an example of aversive conditioning in goldfish. And in this particular experiment, a light came on, and then 5 seconds later, the animal got an annoying shock, And what the goldfish do in anticipation of the annoying shock is they swim around a lot. And so this shows the level of activity during probe trials when there was no shock, and the probe trial stayed on for 45 seconds. And this is averaged over 5 training sessions. So there were 10 trials per session. So as conditioned responding starts to occur, look when it's occurring. It's occurring around the expected time of the unconditioned stimulus. And what seems to be happening is that the peak gets higher and higher, but the timing of the response seems to be there from the beginning. And I'm going to try and convince you in a number of different ways that from the very first conditioned responses, the animal already knows the time. So here, first with the goldfish. Okay, here is one way I will try to convince you. So if, I'm going to show you trial by trial the activity of the animal during the conditioned stimulus. And if the animal doesn't know the time in the beginning, then maybe it'll be active early during the stimulus and then late during the stimulus. But if it knows the time from the very start, then most of the activity as the anticipation develops is going to be toward the end of this cue. All right, so here's, all right. I'll run the macro. So what we're looking at is blocks of 4 trials. And what you can see is that as the conditioned response develops, it shows very nice timing. So that's goldfish. So that's one fish. So we show that in a more formal way by actually modeling these distributions. So here's the 5-second time. And so what we can do is we can see where the peak is, the location of the peak, and how high the peak is, and how spread out the peak is, and things like that, and look at it over trials and see whether the location changes, or if they really do know the time from the start, and same thing with a 15-second time. And when we do that, what we see is the height of the peak does change over trials, but the locations of the peak from the first time we can see a conditioned response don't change. So for the 5-second time, it's maybe it's around 5 seconds, and for the 15-second time, maybe a little bit later, but it's constant. So that's one piece of evidence. Okay, so you say, oh, well, that's goldfish. Maybe they know the time. Here's the mice. So in this particular experiment, a light came on, and we look at when, during this light, which in this case lasted for 8 seconds, does the animal actually start putting its head in and checking for the food. And this is different. This is a slightly different plot. This is a cumulative record of the head poking in different quartiles of the cue. So this is right before the food is presented. This is the beginning of the second half of the cue, and this is the first. These 2 lines represent the first 2 quarters of that cue. And what you can see is from the very first conditioned responses, when the animal is doing the checking is appropriate for the expected time of reinforcement. And acquisition really is time from the start. So what that suggests, these kind of data, is that the animals actually have learned the time prior to showing us any kind of anticipatory response, that temporal learning actually is there before. And there's a wonderful experiment in a preparation that actually shows somewhat slow learning, but it's good for showing that, in fact, they have learned the times prior to showing a conditioned response. And that's eye blink conditioning, which often takes hundreds of pairings before the animals show you eye blinks. In this particular plot, each line represents a trial. And in this case, the blue part is when a tone came on and it was followed by a shock, and the excursions are blinks. So going up like that is a blink. And what you can see is the tone came on, there was a shock, the rabbit blinks, tone, shock, rabbit blinks, so on and so forth. In this case, they used a 700 millisecond ISI. So the time from the onset of the tone until the shock was 700 milliseconds. And after a lot of trials, there's still no blinking during the tone. So when the animal anticipates the shock, the blue part of the line will start to go up before the shock is actually presented. And they do more training, and still no conditioned anticipatory responses. This is just to show you that the rabbit can move its eyelid, but it's clearly not anticipatory. Then what they did, they stopped the experiment before they get the conditioned response, and they start training the animal with a short interstimulus interval, with a 200 millisecond time from the onset of the tone till the shock. And they do that training, though, until they actually get a conditioned anticipatory response. And now the animal is blinking before the shock is presented. Right? So you have a nice anticipatory response. So now they ask the question, in the first part of the experiment, when there was that long cue and the animal wasn't blinking at it, had it learned the time? And so what they do is they just leave the tone on for 750 milliseconds, and if the animal had learned the time, now that it's got this strong response at 250 milliseconds, maybe it'll show a second blink at the time that it had learned but hadn't actually expressed the response. And sure enough, that's what they get, is they get a fair number of trials with the double blinks at the appropriate time. So the animals are actually even learning the time before they're showing you anything about the anticipation. All right, so now the question is, how quickly could times be learned? And we don't know that for too many situations, but here's an example of aversive conditioning from Mike Davis's lab. It's fear potentiated startle, and in this particular experiment, a cue came on, it stayed on for a long time, and in different groups of animals, they were shocked at different intervals. So they were either shocked at 200 milliseconds or 3,200 milliseconds or 51,200 milliseconds, or 51 seconds into the cue. And in fear-potentiated startle, the startle response from an unexpected noise is potentiated if the animal is afraid. So the question is, if you startle the animal at different times during the cue, has the animal learned the time? And even with a single pairing, at least in the case of the one that was 51 seconds into the cue, it looks like the animal may know that time. And with two pairings, already there's evidence in this situation that the animals know the times. So with the potentiated startle has greater potentiation early in the cue, or in the middle of the cue, or toward the end of the cue. Even after 2 trials, and by 5 trials, it's really quite clear. So as the animals move into a situation, they're processing the temporal relationship between these events quite rapidly. And this seems to be true in all kinds of conditioning procedures. And Ralph Miller and his students have done a number of experiments and shown that even when the animals learn conditioned inhibition, they learn times. And so, for example, if you gave one cue and it predicted food 10 seconds later, and then what you do is you have that cue presented and in compound with another cue, the conditioned inhibitor, and no food is presented, then you can ask the question is, when is that inhibition most effective? And it turns out you get the most inhibition at what was the expected time of reinforcement. So even the inhibition seems temporally graded. In overshadowing, you get more overshadowing when the 2 cues signal the same time to the unconditioned stimulus. And there's some evidence in blocking as well that there's temporal specificity, so that the way blocking works is one cue comes to predict an outcome, and then after it predicts it well, there's a second cue that's added that predicts the same outcome, and the responding to the second added cue is diminished. There's not a lot of responding to it. It's blocked. And there's some evidence that it's the fact that the cues signal the same time of reward, not just that they signal reward, but signal the same time of reward, that produces the blocking. Okay, so times are rapidly encoded, and they're learned regardless of contiguity. Conditioned responses are timed, the level of anticipation is inversely related to the delay, and response form can even change with delay. So, and in all of the conditioning procedures, the temporal encoding is implicit. All right, so it's definitely a part of the Pavlovian procedure. But let's turn for a minute and change our question and ask what time is. All right, so what is time? It's how I feel. St. Augustine was baffled, as am I. But actually it turns out that the person who had all the answers 2,000 years ago was actually Aristotle. And here's what Aristotle said about time. He said, there's something by which one distinguishes a greater and a smaller time, and it's reasonable to think that one does this in a way analogous to that in which one discerns spatial magnitudes. So let's take that kind of seriously for a few minutes and see where it takes us. Let's think about the possibility that as an animal experiences a stream of events, that it's extracting the temporal structure in a way that creates a temporal map. Right? And that maybe it even has the properties of spatial maps. So it's in the relationship between things that there's information. Right? So if it's this kind of gestalt relationship between things, what makes us, in a spatial world, what makes us think that things go together? Well, it's the relative spacing, it's the pattern of things. So if the space between rows is relatively greater than the space between columns, we see two rows. And if the relative space between columns is greater than the relative space between rows, most of us will see 4 columns. So, on this view, what makes a CS go with a US is it's somehow the relative relationship between the two makes us see them go together, and association in this view is an after effect of that perception. So if that's true, that it's like a spatial map, then maybe it even has the metric properties of Euclidean space, so that temporal maps survive transformations of scale. And it is the relative relationship. So in a spatial domain, here's a map. And let's say I hide $100 bills underneath the red circles. All right. I could show you the small map, and you could learn that on the small map, and then on the big map you'd have no trouble deciding where it was that you should look. But if I don't preserve the relative relationships, I teach you on the small map here, then you're not quite sure where to look over here. Should you look, say in the same relative position, or should you look under the landmark, under the circle? Right? So how would that work in the temporal domain? Well, in the temporal domain, in a way we've already done that experiment. We've done the contiguity experiment. And so here's an example, right? So there was a 4-second queue, and the time between reinforcements was on average 52 seconds. And we compare what happens with a 4-second queue to an 8-second queue to a 16-second queue, right? And so what we're doing in this case is we're reducing the relative spacing. And I've already showed you what happens. It takes the birds in these auto-shaping experiments longer to see that the key light is a good predictor of the food. Right? So it went from 20 up to 150, as it went from 4 seconds to 32 seconds. So now, what would happen, though, if we had maintained the same relative relationships between cues and food? Now, how would we do that? So what we would do is we would have the 4-second queue, on average 52 seconds between foods, but now we'd have an 8-second queue and we'd double the time between foods. Or we'd have a 16-second queue and quadruple the time between foods. So 208 seconds. And that way we'd maintain the same relative temporal relationship between the cue and the food. And if it's like a temporal map, then it ought to be just as easy for the bird to figure out this is a good cue. The 16-second cue is just as good as the 4-second cue. Right? And sure enough, that's what happens, is whether it's 4, 8, or even 32 seconds, as long as you maintain the same relative spacing, it takes about 20 trials for the bird to figure out this is a good cue. So the time scale invariance implies that the relative spacing determines the strength. Okay, so what's extracted that leads to anticipatory responding? It's the formal extraction of temporal information is what we've been arguing lately. So the argument is that subjects develop an excitatory conditioned response just to the extent that the CS provides information about when the next US is coming. And in a formal sense, you can imagine the animal goes into a context and food happens. And it's unpredictable. It happens at different times. And the animal's quite uncertain, has uncertainty about when that food is going to come. And now a key light comes on and it says, okay, it's coming in 8 seconds. And so it's giving the animal information about when the next food is going to arrive. And this information, that is, the extent to which that key light reduces the animal's uncertainty about when food is going to occur, can actually be computed. There are a group of computational modelers who have really worked out what the uncertainty, the entropy is in various kinds of distributions. And so we borrow from them the idea that there's, depending on the, in a Poisson process, when things are completely unpredictable, that the entropy rate can be computed, and from that entropy rate you can compute the average entropy in a queue. And it's the difference between the average entropy in the background, when the animal's not at all sure what's happening, and the entropy in the trial during the conditioned stimulus, which is the information that the cue provides. And what it boils down to in the end is that it's just the log base 2 over the rate of reinforcement in the trial divided by the rate of reinforcement in the cycle. And so what it says is the information is in the relative time in this kind of computation. All right. And now here's an old plot of a lot of these auto-shaping studies from a lot of different labs. And there were a lot of different CS durations, a lot of different cycle times, and it shows how many pairings it took before the animal treated the key lights as good signals as a function of this ratio of the relative time, the cycle time divided by the trial time. And when you do a regression, amazingly, the slope of that regression line is -1. So you can actually define, empirically define, something that we'll call associability. That is, how fast does the animal learn about this cue, pick up this relationship. And we'll just define it as 1 over the number of pairings it took for reinforcement. And from this relationship, what we see is that the associability of the cue is proportional to the relative time. So there's something about experiencing these events in time. The animal is able to make this computation, and that's what determines the speed of acquisition. Now, a long time ago, people got interested in the idea that it was information that a cue provides about an outcome, which determines how good a conditioned stimulus it is. And these were studies of contingency which were initiated by Riscola in the late 1960s. And they were very important because they also showed that contiguity was not sufficient for learning to occur. So in this case, with some probability, There was aversive conditioning, so a tone would be on for a while, and with some probability a shock would be presented. And in other conditions, the shock was also presented during the intertrial interval in the absence of the unconditioned stimulus. And when the rate of presenting shock in the absence of the cue was equal to that in the presence of the cue, that was the zero contingency or random control procedure. And what was important, the important observation here was that in all these cases, there are the same number of CSUS pairings. So if all that was important was contiguity, you would expect all of these to result in good excitatory conditioning. But in fact, what happened is that the more likely the shock was in the absence of the cue, the less excitatory the cue was. All right? And so people say, well, it has to be, provide information, but I don't think anyone offered a formal way of describing that information. But if you just compute the reduction in uncertainty that the cue provides in Rescola's experiment relative to getting shocked overall, you can do that plot, and even though it's not acquisition scores, which is what we'd really like to have, at least to a first approximation, the degree to which the animal suppresses responding, so lower numbers mean greater conditioning, right, fit pretty well to, pretty linearly related to the number of bits of uncertainty that the cue provides. I mean, the bits of information that the cue provides. So it looks like events are represented in a temporal map. The metric properties of that have the metric properties of a Euclidean space. There's invariance over transformations of scale. The relative spacing of events determines the level of anticipation, and the information determines the associability of cues. And if it really is a temporal map, all right, so the idea so far is that very quickly the animals learn temporal relationships, it exists in a temporal map, then there are other properties of temporal maps that may be similar to spatial maps. And in particular, it may be the case that information can be integrated across experiences. So for example, if you learn to come from your hotel room to this conference room, and then you learn to go from this conference room to the restaurant, you can actually put those two pieces of information together and actually go from your hotel room to the restaurant directly. Right? So there are a couple examples. So here's how it would work in the spatial domain. So let's say, again, I teach you that underneath the circles are the $100 bills. So you look there, and now what I do is I teach you that the triangles are underneath the rectangles. All right? So you want me to go backwards so you get the first one? Okay, and now what I do is I give you a triangle, and I say, where do you want to look for the circle? And look for your $100 bill. And most people will be able to take those two pieces of knowledge and put them together and infer that the rectangle, which had been here, and the circle had been to the right, so they'll look over here for the money. All right. So now how would we do that in the temporal domain? So so first I need to tell you that there's a very reliable finding, which is that when you have forward pairing of a conditioned stimulus with an unconditioned stimulus, you get a strong conditioned response. But if you do backward pairing, you don't get such a strong conditioned response, sometimes no conditioned response. So in this case, what we did was we would give the rat a cue, and it would be followed by food. In this case, it would be food followed by the cue. The click in this case. All right? So that's the first thing you need to know. And when we do that, that's exactly what we find. The ones who get the click followed by food respond a lot. The ones who get food followed, did I say that right? The ones who get the click followed by food respond a lot. The ones who get food followed by the click respond very little to the click. All right? But there was actually another part of the experiment that took place before those pairings. And there was a white noise, in this case, that was forward paired with a click. And then they got forward pairings of the click with the food. All right? And so from an associative point of view, the click is a good cue for food. The white noise is associated with the click, and so they should respond a lot to that. Now, if they have a temporal map, all right, then when will they expect the food? Well, there was a white noise, then there was a click, and then the click was followed by food. So they should, if they put the specific temporal knowledge together, they should expect food out here. And so maybe they'll be a little excited by the click. The interesting group, of course, is the next one. All right, so this group got white noise followed by the click, just like the other group, but it got food first and then click. And they don't respond very much to this click. And so from a traditional associative point of view, they shouldn't respond very much to the white noise because it wasn't really a good cue. Right? So on the other hand, if they can put the two pieces of knowledge together, when do you expect food? You get white noise and click, right? And the food comes just before the click, so if you can actually integrate that, you actually expect the food during the white noise in this case. And that group, in fact, responds more to the cue than the ones who do it after, the ones who get the forward pairings. So contrary to what would be the natural associative prediction, it really does look like they're able to integrate the temporal knowledge across the experience. So to summarize, times are constantly encoded and learned. Event streams are encoded in temporal maps. The information extracted from relative spacing determines the strength and the form of anticipation. Information in these maps can be integrated across experiences. So, perhaps, learning temporal relationships is what we usually mean by associative learning. Thank you. Well?
Peter, you make a compelling case that interstimulus intervals that we think of as too long for learning to occur do in fact support learning. But I completely agree with you, but I do feel there has to be some limit to that. Will the CS that occurs in January be linked to the US that occurs in March?
Well, I'm not sure what the limits of the temporal learning are. It would be nice to know them. And surely there must be some limit to it. On the other hand, another way of looking at it is that animals, including us, experience a stream of events. And those events are encoded, and as they're encoded, there is knowledge about when they occurred in time. And that's what's learned. Then later on, when I ask you to tell me what the temporal relationships is because of the demands of a particular task, you're usually quite able to do that. So it may be that the temporal relationship between things really is there, but it may not be that easy. I have to figure out how to ask you whether you know it. That's the question. Yeah.
Tim? Here, I wonder, taking this last piece here, in the earlier data you showed that they were encoding time very early, and then the magnitude of the response is getting bigger, their arousal is increasing. So I'm wondering about the second piece here that is sort of using your informational approach to get the value transfer that has to happen, the valence of the stimulus. It seems like that piece still has to be there, but it seems like it'd be really tough to do with that informational account because coding that valence information somehow seems a lot harder to be than coding the temporal information. Does that make any sense?
Well, I'm not saying that the only thing that's learned is time. Right. Clearly, they learn about all sorts of attributes, including hedonic attributes. But again, I think one of the points is that it may appear to be slow learning, but it only appears to be slow because we're looking for a particular anticipatory response. And in fact, it may not be so slow in any of those. Ben?
I'm wondering if you would be able to apply the timing notion to the very well-known famous failures to learn simultaneous discrimination. So if you go back to the old Rice experiment, if delays have any duration at all, we fail to learn the discrimination. Doesn't experiments like that make a case that you really need the traditional concept of association, the concept of contiguity, and also the concept of association?
Can you say some more about the particulars of the experiment?
Well, the Price experiment was brightness discrimination, good choice, with Y names, basically. And what they found was that the delays were longer than 3 or 4 seconds, and the animal was completely unable to respond to the pressure.
I guess I'd have to think about the particular example, but one of the messages, right, is that the mapping of the knowledge about when an outcome is going to occur doesn't always translate into the response that you wish you could measure. So even though the point I think was made earlier, Peter Colleen was making the point earlier, that there really is a mapping between different modes of operation and different specific responses. And it could be that in this situation, whatever is going on just doesn't translate into increasing the likelihood of the operant response.
Well, they always respond. They just respond non-differentially.
I don't know. I'll have to think about it.
Well, Peter,
Ron?
I think you've already handled this issue in a couple of ways. One is that we don't know in this experiment what the ratio of the delay to the intertrial interval was. We don't know in what ways, what other responses the animal might be making in Grice's experiments. I mean, your experiments, when you control either of those, you've got success with monopoly. So I think you really have answered this question.
Well, I think we have to really understand better how an anticipatory response maps into the performance of this operant response to really know.
This is the most convincing evidence I've seen in favor of the temporal idea.
Thank you. Any more? All right. Have a good evening, everyone.